Tonight, before we begin this journey together, let me ask you one simple question. What if every illustration of our solar system you've ever seen was wrong? What if the familiar image printed in textbooks, displayed in museums, and taught in classrooms for generations, a beautiful, nearly perfect spherical bubble surrounding the sun, was never the true shape of our cosmic home? What if the edge of the solar system isn't where we think it is? What if it doesn't even stay in the same place? And what if, at this very moment, the invisible frontier separating our sun from the rest of the Milky Way is quietly expanding, shrinking, and breathing? For decades, humanity believed it understood the broad outline of the solar system. We knew the planets. We mapped their orbits. We landed on the moon. We explored Mars. We sent probes to Jupiter, Saturn, Uranus, and Neptune. With each new mission, our confidence grew. It seemed that although countless mysteries remained, at least one thing appeared certain. The solar system was enclosed within a giant, roughly spherical protective bubble created by the sun itself. It was elegant. It was simple. And, as it turns out, it was only part of the story. Because sometimes the universe waits patiently for us to become comfortable with an idea before revealing that reality is far stranger than imagination. Tonight, we will follow two silent travelers that have spent nearly half a century racing away from Earth. They carry no crew, no captain, no chance of ever returning home. Yet these lonely machines have transformed our understanding of where the solar system truly ends. They are Voyager 1 and Voyager 2. Before we continue, if you enjoy long-form space documentaries that explore the deepest mysteries of our universe, consider subscribing to the channel. It truly helps us create more documentaries like this. And, while you're listening, leave a comment telling us where in the world you're joining this journey from. It's always fascinating to see people from every continent gathering together to explore the universe. Now, let's travel farther from Earth than any human-made object has ever gone. In 1977, NASA launched two spacecraft only 16 days apart. Their original mission was ambitious but limited: visit the giant planets, study Jupiter, Saturn. Then, for Voyager 2 alone, continue toward Uranus and Neptune. No one expected these spacecraft to become humanity's first ambassadors to interstellar space. No one imagined they would still be operating nearly 50 years later. Powered by small radioisotope generators, carrying computers far less powerful than today's smartphones, Voyager 1 and Voyager 2 began a journey unlike any before them. They crossed the asteroid belt. They revealed volcanoes erupting on Jupiter's moon, Io. They discovered unexpected structures in Saturn's rings. They transformed our understanding of Uranus and Neptune. With every billion miles they traveled, their scientific mission expanded. Eventually, they reached a destination no spacecraft had ever approached: the outer frontier of the sun's influence, the place where our star slowly surrenders control to the immense forces of the Milky Way. For generations, this boundary had remained invisible. No telescope could photograph it. No astronaut could visit it. Scientists could only estimate where it might exist. It was thought to resemble a vast bubble surrounding every planet, every comet, and every spacecraft born under the sun. A nearly perfect sphere. Simple, symmetrical, comfortingly familiar. That image appeared everywhere: scientific illustrations, planetarium shows, children's textbooks, television documentaries. Even professional models often portrayed the solar system enclosed within a smooth, rounded shell. It seemed logical. After all, the sun radiates energy outward in every direction. Its solar wind, a continuous stream of charged particles, flows across the solar system like an invisible hurricane. If the sun pushes equally in every direction, wouldn't the resulting boundary naturally form a sphere? For decades, that assumption appeared perfectly reasonable. There was just one problem. No one had ever actually measured the boundary itself. Science often begins with elegant assumptions, but assumptions must eventually face reality. And reality has a habit of refusing to behave exactly as expected. As Voyager continued its lonely voyage into darkness, the spacecraft carried instruments capable of measuring something our eyes never could: magnetic fields, charged particles, plasma density, cosmic radiation, invisible clues hidden within the emptiness of space. Slowly, patiently, year after year, those instruments gathered data from regions no human technology had ever explored. Nothing dramatic happened overnight. There was no giant wall waiting at the edge of the solar system, no glowing barrier, no visible frontier. Instead, the spacecraft entered an environment where tiny changes began appearing inside streams of numbers transmitted across billions of miles. To most people, those numbers meant nothing. To scientists, they were astonishing. The behavior of charged particles began changing. The magnetic environment shifted. Cosmic rays arriving from deep within the galaxy suddenly became far more abundant. Meanwhile, particles originating from the sun rapidly declined. It was as though Voyager were slowly stepping from one invisible ocean into another. Then came the moment that changed everything. Voyager had reached the heliopause, the outer boundary of the sun's enormous protective bubble. The first spacecraft in history to enter interstellar space. It should have confirmed the old picture. Instead, it challenged it. When researchers compared measurements from Voyager 1 with those from Voyager 2, something unexpected emerged. The boundary was not located at the same distance in different directions. One spacecraft encountered it much sooner than the other. That difference could not simply be dismissed as measurement error. Something enormous was reshaping the solar system itself. The invisible bubble surrounding our planetary neighborhood was not perfectly round. One side appeared compressed. Another stretched much farther into space. Instead of resembling a sphere, the solar system looked increasingly like a gigantic droplet moving through an invisible cosmic wind. Even more surprising, the boundary itself refused to remain still. Scientists discovered evidence suggesting that it expands and contracts over time. As the sun's activity rises and falls during its approximately 11-year cycle, the entire protective bubble breathes. Sometimes it swells outward. Sometimes it shrinks inward. The frontier itself moves. Incredibly, Voyager 1 may have crossed this shifting boundary more than once as it fluctuated around the spacecraft. Imagine standing on the shoreline while waves repeatedly advance and retreat around your feet. One moment you are standing on dry sand. The next, seawater surrounds you again. The edge is not fixed. It lives. The solar system behaves in a remarkably similar way. This realization forced scientists to rethink decades of assumptions. The boundary surrounding our planetary system is not a rigid shell. It is a dynamic structure continuously shaped by the interaction between our sun and the galaxy beyond. It bends, it flexes, it responds to forces operating across unimaginable distances. Suddenly, the solar system seemed less like an isolated island and more like a ship sailing through an immense cosmic ocean. The sun itself is not standing still. Together with every planet, moon, asteroid, and comet, it races around the center of the Milky Way at roughly 515,000 miles per hour, carrying the entire solar system through a constantly changing interstellar environment. As our star plows through thin clouds of gas, magnetic fields, and energetic particles drifting between the stars, those external forces push back against the outward pressure of the solar wind. The result is not perfect symmetry. It is constant negotiation, an invisible battle between the power of our own star and the pressure of the galaxy itself. Every second, that battle reshapes the frontier surrounding everything we have ever known: Earth, Mars, Jupiter, Saturn, even the distant Voyager spacecraft. The farther scientists looked into the Voyager data, the more they realized that the old textbook picture could no longer survive. The map was wrong, not disastrously wrong, but incomplete. Reality proved richer, more dynamic, more beautiful. The familiar image of a perfect cosmic bubble gave way to something alive with motion, a vast structure sculpted by magnetic fields, plasma flows, and the ceaseless movement of our sun through the Milky Way. It is one of the greatest discoveries ever made without anyone seeing it directly. Because the true shape of the solar system cannot be photographed with a single camera. It must be reconstructed from whispers carried by particles, from invisible magnetic fields, and from the lonely signals of two spacecraft still traveling into the darkness. In the chapters ahead, we will follow those signals. We will discover what the heliosphere truly is, how the solar wind builds an invisible shield around our planetary system, why the edge of that shield refuses to remain fixed, how the Milky Way itself pushes against our sun, and why the greatest map of our cosmic neighborhood is still being drawn today. Because the boundary of the solar system is not simply the place where the sun ends. It is the place where humanity's understanding of its place in the galaxy truly begins. For most of human history, the sun appeared deceptively simple. A brilliant golden disk rising every morning, a source of warmth, a giver of light, the center of our planetary family. From Earth, it seems calm and constant, changing little from one day to the next. But appearances can be profoundly misleading. The sun is not a quiet celestial lamp suspended in space. It is an immense nuclear furnace, a sphere of superheated plasma nearly 865,000 miles across, where hydrogen atoms fuse into helium every second, releasing unimaginable amounts of energy. Deep within its core, temperatures reach approximately 27 million degrees Fahrenheit. The pressure is so extreme that matter behaves unlike anything we experience on Earth. Energy born in the core slowly works its way outward, taking thousands, sometimes hundreds of thousands of years to reach the visible surface. Yet once it arrives, the sun never truly rests. Its surface boils continuously. Gigantic arcs of plasma rise and collapse. Magnetic fields twist themselves into impossible shapes. Explosive eruptions launch billions of tons of charged particles into space. To the naked eye, sunlight appears peaceful. To a spacecraft observing in ultraviolet and X-ray wavelengths, the sun resembles a living ocean of fire. It is from this restless star that one of the solar system's most remarkable structures is born, the solar wind. Despite its name, the solar wind is nothing like the air moving across Earth's atmosphere. There is no oxygen, no breeze, no sound. Instead, it is an endless stream of electrically charged particles flowing outward from the sun in every direction. These particles are primarily electrons and protons, mixed with heavier atomic nuclei that have been stripped of their electrons. Together, they form what physicists call plasma. Plasma is often described as the fourth state of matter. Unlike solids, liquids, or gases, plasma consists of atoms so energetic that electrons are no longer bound to their nuclei. The result is an electrically conducting fluid that responds dramatically to magnetic fields. Remarkably, plasma is the most common form of ordinary matter in the observable universe. Stars are plasma. Nebulae are plasma. Much of the space between galaxies contains plasma. Even the solar wind sweeping across our planetary system is an ocean of plasma so thin that it would be considered a near-perfect vacuum by laboratory standards. Every second, the sun ejects millions of tons of this material into space. Unlike a single explosive eruption, the solar wind never stops. It is continuous, relentless, a permanent outflow driven by the extreme temperatures of the sun's outer atmosphere, known as the corona. One of the enduring mysteries of solar physics is that the corona is vastly hotter than the visible surface beneath it. While the sun's surface measures roughly 10,000 degrees Fahrenheit, Portions of the corona reach several million degrees. Exactly how the corona becomes so hot remains an active area of research, involving magnetic reconnection, wave heating, and other complex plasma processes. Whatever the mechanism, this extraordinary heat gives particles enough energy to escape the sun's gravitational pull. Once released, they accelerate outward into the darkness. Near Earth, the solar wind typically travels between 250 and 500 miles per second, although powerful solar storms can propel particles much faster. At those speeds, the solar wind reaches our planet in only a few days, yet Earth is merely one stop along a much longer journey. The particles continue racing outward past Mars, beyond Jupiter, across Saturn, through the realm of Uranus and Neptune, far beyond Pluto. Still they continue. Although the solar wind gradually becomes thinner as it spreads across greater distances, it never simply disappears. Instead, it fills an enormous region surrounding the sun. Imagine placing a powerful fountain at the center of a vast field. Water sprays outward in every direction. As it expands, the flow becomes thinner. Yet it continues occupying an ever-growing volume. The solar wind behaves similarly, except the distances involved are almost beyond comprehension. Rather than filling a garden, it fills billions of miles of interplanetary space. This immense bubble of solar influence is known as the heliosphere. The heliosphere is not a physical shell. It has no walls, no visible surface. It cannot be photographed directly with ordinary cameras. Instead, it is an invisible region where the outward pressure of the solar wind dominates the surrounding environment. Every planet in our solar system resides inside this enormous bubble. Every asteroid, every comet that spends most of its orbit near the sun, every spacecraft humanity has ever launched. Even Voyager 1 and Voyager 2 spent decades traveling within it before finally reaching its distant edge. If the sun were suddenly switched off, an impossible scenario, but useful for imagination, the heliosphere would eventually collapse. Its existence depends entirely upon the continuous flow of solar plasma streaming outward into interstellar space. In many ways, the heliosphere functions as the solar system's largest atmosphere. Not an atmosphere of breathable air, but an atmosphere of plasma, magnetic fields, and flowing charged particles extending far beyond the planets themselves. Yet its greatest importance lies not in what it contains, it lies in what it keeps out. The Milky Way is far from empty. Between the stars travel extraordinarily energetic particles known as galactic cosmic rays. These particles originate from some of the most violent events in the universe: supernova explosions, rapidly rotating neutron stars, powerful shock waves, possibly even the environment surrounding black holes. Accelerated to velocities approaching the speed of light, cosmic rays race across the galaxy for millions of years. Some consist of solitary protons. Others are atomic nuclei stripped completely bare. When they collide with matter, they can penetrate deep into biological tissue, damage DNA, disrupt electronics, and trigger complex chains of nuclear interactions. On Earth, our atmosphere and magnetic field absorb most of these particles before they reach the surface. Without those protective layers, life would face a vastly harsher radiation environment. Yet Earth's defenses are only part of the story. Long before cosmic rays encounter our planet, many of them encounter something much larger: the heliosphere itself. As the solar wind streams outward, it carries the sun's magnetic field with it. Because the sun rotates, these magnetic field lines do not extend straight outward. Instead, they twist into a gigantic spiral pattern known as the Parker spiral, named after solar physicist Eugene Parker. This enormous magnetic structure fills the heliosphere like invisible threads woven throughout an immense bubble. Charged particles moving through magnetic fields rarely travel in straight lines. Instead, they bend, scatter, spiral. Many incoming cosmic rays are deflected, slowed, or prevented from penetrating deeply into the solar system. The heliosphere does not stop every cosmic ray. Some still reach Earth. Others pass through to the inner planets. But the overall intensity is significantly reduced. Without this vast magnetic shield, radiation levels throughout the solar system would be dramatically higher. Astronauts traveling beyond Earth's protective magnetosphere would face even greater risks. Electronic systems aboard spacecraft would endure more frequent damage. Over geological timescales, planetary environments themselves might evolve differently. The heliosphere, therefore, acts as an enormous first line of defense. To appreciate its scale, consider Earth's own magnetic shield. Our planet generates a magnetosphere extending tens of thousands of miles into space. This invisible cocoon deflects charged particles from the Sun, protecting our atmosphere from gradual erosion. Without Earth's magnetosphere, the solar wind would interact far more directly with the upper atmosphere, as appears to have happened on Mars after it lost most of its global magnetic field billions of years ago. The heliosphere performs a remarkably similar function. Only instead of protecting a single planet, it protects an entire planetary system. Earth's magnetosphere spans tens of thousands of miles. The heliosphere stretches for well over 100 astronomical units in some directions, billions upon billions of miles across. It is, in effect, the solar system's magnetosphere, a protective cocoon surrounding every major planet simultaneously. Nested shields exist throughout our cosmic neighborhood. Earth protects us locally. The heliosphere protects us regionally. Beyond both lies the vast and far more hostile environment of interstellar space. For centuries, humans imagined outer space as a silent vacuum. Modern astronomy has revealed something much richer. Space is filled with invisible rivers of plasma, magnetic fields, shock waves, radiation, charged particles born from exploding stars and traveling unimaginable distances. The heliosphere represents the constantly shifting boundary where our Sun pushes back against that immense galactic environment. It is not merely a bubble. It is an active frontier, a dynamic balance between two competing domains. Inside, the solar wind dominates. Outside, the galaxy takes control. The remarkable part is that this balance never remains perfectly steady. The Sun itself changes. Its magnetic field reverses approximately every 11 years. Solar activity rises toward periods known as solar maximum, producing more sunspots, solar flares, and coronal mass ejections. Then activity gradually declines towards solar minimum, when the Sun becomes comparatively quiet. These changes alter the strength of the solar wind flowing into space. As the pressure of that wind increases or decreases, the heliosphere responds. It expands. It contracts. It shifts. The solar system's protective bubble is not frozen in place. It breathes. Like the beating heart of a living organism, it slowly pulses over time. Those subtle motions become enormously important near the distant edge of the heliosphere. There, even relatively small changes in solar pressure can move the boundary millions of miles. It was precisely these slow, invisible movements that Voyager would eventually detect. The spacecraft were not simply traveling toward a fixed destination. They were approaching a frontier that itself was constantly moving, a shoreline shaped by the changing activity of our own star. Everything we have explored so far reveals a profound truth. The solar system is not isolated. It is not enclosed within a rigid shell, suspended in empty space. Instead, it exists inside a vast magnetic bubble continuously sculpted by the interaction between the Sun and the galaxy beyond. Every second, trillions upon trillions of charged particles stream outward from our star, carrying energy, momentum, and magnetic fields across billions of miles. Without realizing it, every human being has lived their entire life inside this invisible shield. Every civilization in recorded history, every spacecraft ever launched, every signal ever transmitted from Earth. all have existed beneath the protection of the heliosphere. Yet every shield has an edge. Eventually, the outward pressure of the solar wind weakens enough that the surrounding galaxy begins pushing back. There, at the farthest frontier of the sun's influence, lies one of the most extraordinary boundaries in the universe. A place where the solar system gradually gives way to interstellar space. In the next chapter, we will travel to that invisible frontier itself, the heliopause, where Voyager first crossed from the domain of our sun into the vast ocean between the stars. After traveling through the vast protective bubble of the heliosphere, we eventually arrive at a question that seems almost impossible to answer. Where does the solar system actually end? At first, the answer appears obvious. Surely there must be a line, a boundary, a final wall separating the influence of our sun from the immense emptiness between the stars. For centuries, human imagination has pictured frontiers as visible things. The shoreline where land meets the sea, a mountain ridge dividing two valleys, a border marked by fences or walls. But nature rarely draws such simple lines, especially in space. Out beyond the orbit of Pluto, where sunlight has become little more than an unusually bright star, there exists no glowing barrier waiting for an approaching spacecraft. No gigantic shell surrounds the solar system. No invisible force suddenly pushes a probe backward. Instead, the transition from the sun's domain to interstellar space unfolds gradually through a series of enormous plasma regions, each governed by the balance between two invisible but immensely powerful forces. To understand the heliopause, we must first encounter another remarkable frontier, the termination shock. Imagine a jet aircraft flying faster than the speed of sound. As it slices through Earth's atmosphere, pressure waves can no longer move ahead of the aircraft quickly enough. They pile up into a shock wave. The familiar sonic boom is born. Something surprisingly similar happens in space. For billions of miles, the solar wind streams outward from the sun at astonishing speeds. Near Earth's orbit, these charged particles typically travel between 250 and 500 miles per second. They remain supersonic relative to the plasma through which they move. Nothing appears capable of slowing them until they begin encountering the growing pressure of the interstellar medium. Far from the sun, the outward-flowing plasma can no longer continue expanding freely. The surrounding galaxy pushes back. Gradually, the solar wind begins losing momentum. Eventually, it reaches a critical point. Its speed suddenly drops from supersonic to subsonic. This enormous transition zone is called the termination shock. Unlike the shock wave surrounding an aircraft, the termination shock is unimaginably vast. It stretches across the entire solar system, not as a rigid shell, but as a complex, constantly changing region where flowing plasma abruptly slows and compresses. When Voyager 1 crossed the termination shock in late 2004, its instruments detected exactly what theory had predicted. The solar wind slowed dramatically. Magnetic turbulence increased. Energetic particles behaved in unexpected ways. Scientists realized that humanity had entered a region never before explored. Yet this was not the end of the solar system. It was only the beginning of its outer frontier. Beyond the termination shock lies a vast region known as the heliosheath. If the heliosphere is the sun's protective bubble, then the heliosheath functions as its outer cushioning layer. Here, the once fast solar wind has already slowed considerably. Unable to continue racing freely outward, the plasma becomes hotter, denser, and far more turbulent. Imagine a river flowing rapidly downstream. As it approaches the ocean, the current weakens. Water begins swirling into countless eddies. Different currents collide. The once orderly flow becomes chaotic. The heliosheath behaves in much the same way. Charged particles interact continuously with magnetic fields. Shock waves travel through enormous distances. Plasma compresses, twists, and changes direction. This region acts as a gigantic buffer, separating the relatively organized environment dominated by the Sun from the far more complex conditions of interstellar space. It is anything but empty. Although the density of matter remains extraordinarily low by earthly standards, the heliosheath is filled with invisible activity. Every second, trillions of charged particles interact in ways governed by plasma physics rather than ordinary fluid mechanics. The farther Voyager traveled through this turbulent region, the closer it came to one of the greatest milestones in the history of space exploration: the heliopause. The heliopause is often described as the edge of the solar system. Strictly speaking, that statement is only partially correct. The planets continue far inside it. The distant Oort cloud likely extends far beyond it. Gravity from the Sun reaches infinitely far into space, gradually weakening with distance. The heliopause is not the edge of the Sun's gravity. It is the edge of the Sun's plasma influence. Here, the outward pressure generated by the solar wind is finally balanced by the pressure of the interstellar medium. Neither side dominates completely. Instead, an invisible equilibrium emerges. Inside the heliopause, the solar wind controls the environment. Outside it, the galaxy takes over. This makes the heliopause one of the most important physical boundaries in the universe. It separates two entirely different cosmic environments, one created by our own star, the other shaped by the Milky Way itself. Yet calling it a boundary can be misleading. The heliopause is not a solid surface. No spacecraft crashes into it. No camera photographs a visible wall. If an astronaut somehow stood there, a completely impossible scenario, nothing would appear different to the naked eye. Space would still look black. The distant stars would shine exactly as before. The heliopause exists not because we can see it, but because instruments can measure it. It is defined by changes in plasma, magnetic fields, and energetic particles rather than visible objects. In many ways, it resembles the boundary between two enormous weather systems. There is no physical wall separating warm air from cold air on Earth. Yet meteorologists can identify exactly where one air mass ends and another begins. The heliopause functions similarly, except its weather consists of charged particles moving across billions of miles. On one side flows plasma born inside the Sun. On the other drifts plasma that has traveled through the galaxy for millions of years. At the heliopause, these two immense environments press against one another. They do not violently crash together like ocean waves striking a cliff. Instead, they negotiate. Each pushes continuously against the other. The result is a dynamic interface that shifts as conditions change. One of the most fascinating aspects of this frontier is that plasma from both regions behaves very differently. Inside the heliosphere, the plasma originates almost entirely from the Sun. It carries the solar magnetic field outward in the familiar Parker spiral. The particles generally move away from the Sun. Outside the heliopause, however, the plasma belongs to the local interstellar medium. Its magnetic field has an entirely different orientation. Its particles have different temperatures, different densities, different origins. Some of this material may have spent millions of years drifting between stars before ever encountering our solar system. Where these two environments meet, neither immediately replaces the other. Instead, magnetic fields interact. Particles scatter. Energy transfers gradually across the boundary. Understanding this interaction remains one of the most challenging problems in heliophysics today. Fortunately, Voyager carried precisely the instruments needed to investigate it. Neither spacecraft possessed cameras capable of photographing the heliopause directly. They did not need them. Their scientific instruments were far more valuable. Among the most important were magnetometers capable of measuring tiny changes in magnetic field strength and direction. Cosmic ray detectors monitored energetic particles arriving from both the Sun and deep space. The plasma wave science instrument measured oscillations traveling through ionized gas. Together, these instruments transformed invisible physics into measurable data. As Voyager approached the heliopause, scientists watched the incoming numbers with growing excitement. One of the first major changes involved energetic particles. Solar particles streaming outward declined dramatically. Meanwhile, galactic cosmic rays arriving from interstellar space suddenly increased. The spacecraft was leaving one particle environment and entering another. Then came another crucial observation. The density of plasma unexpectedly increased. At first glance, this seemed counterintuitive. Wouldn't empty interstellar space contain less material? Surprisingly, the opposite proved true. The plasma surrounding the heliopause outside the solar system was significantly denser than the extremely expanded solar wind inside. Voyager detected this increase indirectly through plasma wave oscillations generated by distant solar eruptions traveling outward across billions of miles. By measuring the frequency of those waves, scientists calculated the surrounding plasma density with remarkable precision. The result was unmistakable. Voyager had entered a different environment altogether. Perhaps the most carefully examined evidence involved magnetic fields. Researchers initially expected the magnetic field direction to rotate dramatically upon crossing the heliopause. Instead, something unexpected happened. The magnetic field remained surprisingly well aligned across the boundary. At first, this puzzled scientists. Had Voyager truly entered interstellar space? Or was it somehow still inside the heliosphere? Years of careful analysis gradually resolved the mystery. Although the overall field direction changed less than anticipated, its strength, particle environment, plasma density, and numerous other measurements all pointed toward the same conclusion. The spacecraft had indeed crossed the heliopause. The apparently smooth magnetic transition reflected the geometry of the local interstellar magnetic field rather than a failure of the original interpretation. Science rarely advances through one dramatic observation. Instead, confidence grows as multiple independent measurements converge upon the same answer. That is exactly what happened here. No single instrument alone proved Voyager had entered interstellar space. Together, however, the evidence became overwhelming. Solar energetic particles nearly vanished. Galactic cosmic rays increased substantially. Plasma density matched interstellar expectations. Magnetic measurements supported a new physical environment. Every major indicator pointed in the same direction. Humanity's first spacecraft had crossed the boundary between the Sun and the galaxy. On August 25, 2012, Voyager 1 officially entered interstellar space. Nearly 6 years later, Voyager 2 crossed the heliopause as well. The second crossing proved every bit as important as the first. Because the two spacecraft traveled in different directions, scientists could compare completely independent measurements. They discovered that the heliopause did not lie at exactly the same distance from the Sun. Voyager 2 encountered it significantly closer than Voyager 1 had. Immediately, an even deeper mystery emerged. If the heliopause were a perfect sphere, both spacecraft should have crossed at roughly equal distances. They did not. The solar system itself appeared asymmetrical. Its protective bubble had been distorted, compressed in one region, extended in another. The elegant textbook diagrams could no longer describe reality. The heliopause had revealed something astonishing. The solar system is not enclosed inside a perfectly round shell. Instead, it exists within an enormous structure continuously shaped by both the Sun and the galaxy beyond. The boundary itself bends, moves, responds. It is alive with plasma, magnetic fields, and invisible forces operating across billions of miles. The heliopause was never the simple edge scientists once imagined. It is a living frontier, and the deeper Voyager ventured beyond it, the more surprising that frontier became. because discovering where the solar system ends turned out to be only the beginning. The next mystery was even greater. Why does the entire boundary appear warped, compressed, and stretched into a shape no one expected? For generations, one image quietly shaped humanity's understanding of the solar system. It appeared in classrooms, science museums, encyclopedias, television documentaries, even scientific illustrations. A glowing sun rested at the center of a vast, nearly perfect bubble. Inside that bubble orbited every planet, asteroid, comet, and spacecraft. Outside lay the immense darkness between the stars. The image was elegant, symmetrical, easy to understand, and for many years it represented the best scientific picture available. But there was one important detail hidden beneath every illustration. It was never an observation. It was a model, a reasonable approximation built from limited information. Like every scientific model, it remained provisional, accurate until better evidence appeared. That evidence would eventually arrive from farther away than any human-made object had ever traveled. And when it did, one of the most familiar images in astronomy began to fall apart. The heliosphere was not the perfect sphere everyone imagined. It was something far stranger, something constantly reshaped by invisible forces stretching across the Milky Way itself. To understand why, we must first stop thinking of the solar system as standing still. Nothing in the universe is truly motionless. Earth circles the Sun at nearly 67,000 miles per hour. The Moon orbits Earth. The planets follow their own paths around our star. Yet even the Sun is only one traveler among hundreds of billions of stars. Together with every planet in its gravitational family, the Sun races around the center of the Milky Way at roughly 515,000 miles per hour, completing one galactic orbit approximately every 230 million years. Every mountain on Earth, every ocean, every living creature, every human civilization that has ever existed has been carried along on this extraordinary journey through the galaxy. Although we cannot feel that motion, the solar system is constantly moving through the thin gas, dust, plasma, and magnetic fields that fill interstellar space. This realization changes everything. Imagine placing your hand outside the window of a moving car. Even on a calm day, your hand feels wind pressing against it. The faster the car moves, the stronger that pressure becomes. The air itself is not chasing the vehicle. The motion of the vehicle creates the apparent wind. Something remarkably similar happens on a cosmic scale. The Sun moves through the local interstellar medium, an immense region filled with extremely diffuse hydrogen, helium, charged particles, and magnetic fields, left behind by countless generations of stars. Although this material is extraordinarily sparse by earthly standards, it is not empty, and over distances measured in billions of miles, even tiny pressures become enormously important. The heliosphere is therefore not expanding into a perfect vacuum. It is pushing against an environment that pushes back. This interaction creates one of the most fascinating examples of pressure balance in astrophysics. Inside the heliosphere, the solar wind streams relentlessly outward. Outside, the interstellar medium exerts its own pressure inward. Where these opposing forces meet, the boundary takes shape. But because the Sun is moving through the galaxy, that pressure is not equal in every direction. The front of the heliosphere experiences a stronger headwind. The rear experiences much less resistance. Immediately, symmetry disappears. The front becomes compressed. The back stretches outward. The solar system begins to resemble a boat moving through water. Anyone watching a ship cut across a quiet lake notices the same pattern. At the bow, water piles up. At the stern, a long wake trails behind. The boat itself remains unchanged. Its surrounding environment does not. The heliosphere behaves in a surprisingly similar manner. The bow of the solar system, the direction in which the Sun moves through the galaxy, faces continuous pressure from interstellar plasma and magnetic fields. Meanwhile, the opposite side extends far behind the Sun, creating an elongated tail that may stretch for hundreds of astronomical units. Early scientific illustrations often compared this shape to a comet. Just as a comet develops a long tail pointing away from the Sun, the heliosphere appeared to develop an enormous trailing region pointing away from the direction of galactic motion. For years, this became the dominant picture. Yet even that interpretation would later prove incomplete. As computer simulations became increasingly sophisticated, researchers discovered that the heliosphere might not resemble a simple comet at all. Its true geometry could be even more complicated. Much of this progress became possible through advances in magnetohydrodynamics, commonly abbreviated as MHD. Magnetohydrodynamics combines fluid dynamics with electromagnetism to describe how electrically conducting fluids, such as plasma, behave under the influence of magnetic fields. Unlike ordinary air or water, plasma cannot be understood by pressure and velocity alone. Its charged particles constantly interact with magnetic forces. Field lines twist, reconnect, stretch, store energy, release energy. The result is an environment far more dynamic than classical fluids. Modern supercomputers now solve millions of mathematical equations simultaneously to simulate these interactions. Researchers feed the models with measurements of solar wind speed, magnetic field strength, plasma density, and the properties of the surrounding interstellar medium. The simulations then evolve according to the laws of physics. What emerged surprised many scientists. Rather than producing a smooth, perfectly rounded bubble, the models generated distorted, asymmetrical structures. Some resembled elongated droplets. Others appeared flattened at the nose. Still others developed two broad plasma jets extending behind the Sun instead of one long comet-like tail. Different assumptions produced different shapes. Each remained consistent with portions of the available data. The debate intensified. Then came the observations from Voyager. Voyager 1 and Voyager 2 were traveling in completely different directions. Voyager 1 moved generally north of the ecliptic plane. Voyager 2 headed south. This difference proved invaluable. If the heliosphere truly possessed perfect symmetry, both spacecraft should have encountered its outer boundaries at nearly identical distances. Instead, something unexpected occurred. Voyager 1 crossed the heliopause at approximately 121.6 astronomical units from the Sun in August 2012. Voyager 2 crossed it at roughly 119 astronomical units in November 2018. A difference of only a few astronomical units may sound insignificant. In reality, 1 astronomical unit equals nearly 93 million miles. The discrepancy represented hundreds of millions of miles. The boundary surrounding the solar system clearly did not lie at the same distance in every direction. Initially, some researchers wondered whether the difference resulted from the changing solar cycle. After all, 6 years separated the two crossings. During that time, the heliosphere itself expanded and contracted. Perhaps the boundary had simply moved. That explanation accounted for part of the discrepancy, but not all of it. Even after correcting for solar activity, evidence continued pointing toward a fundamentally asymmetrical heliosphere. The solar system itself appeared misshapen. Additional clues came from NASA's Interstellar Boundary Explorer, or IBEX. Unlike Voyager, which sampled only narrow paths through space, IBEX remotely detected energetic neutral atoms arriving from every direction around the heliosphere. Its observations revealed an unexpected structure known as the IBEX ribbon, a mysterious arc of enhanced energetic particles stretching across the sky. The ribbon suggested that the local interstellar magnetic field plays a far greater role in shaping the heliosphere than scientists had previously believed. Rather than simply compressing the front like wind against a balloon, The galaxy's magnetic field appears to guide plasma flows along preferred directions. The boundary is therefore influenced not only by pressure, but by magnetism itself. Later observations strengthen this picture. Computer simulations incorporating realistic magnetic fields produced heliospheres that differed dramatically from earlier spherical models. Some became noticeably flattened, others twisted. Some developed asymmetrical lobes. The heliosphere increasingly resembled a living magnetic structure rather than a smooth geometric object. Yet despite these advances, one remarkable fact remains. No scientist has ever directly photographed the heliosphere from the outside. Such an image is currently impossible. Every model relies upon indirect measurements. Voyager samples only two narrow trajectories. IBEX observes energetic neutral atoms. Ground-based telescopes contribute additional constraints. Supercomputer simulations fill in the remaining gaps. Like detectives reconstructing a crime scene from scattered evidence, heliophysicists assemble the most likely picture using every clue available. This explains why debates about the heliosphere's exact shape have continued for decades. Some researchers still favor a long comet-like tail. Others argue for a croissant-shaped heliosphere with two large plasma lobes extending behind the Sun. Still others propose intermediate geometries depending upon changing solar conditions. None of these disagreements imply that science is uncertain about the heliosphere's existence. Rather, they reflect the extraordinary complexity of plasma physics operating across distances that dwarf the solar system itself. One lesson has already become unmistakably clear. The textbook sphere is gone. Reality is more complicated, more dynamic, more beautiful. The heliosphere is not a static balloon frozen in space. It is continuously sculpted by the solar wind, magnetic fields, interstellar plasma, and the Sun's relentless journey through the Milky Way. Its shape evolves, its boundaries shift. Its asymmetry records the invisible interaction between our star and the galaxy surrounding it. In many ways, the heliosphere resembles a windsock at an airport. A windsock never possesses a single permanent shape. It expands, collapses, twists, leans. Its appearance changes with every shift in the wind. Yet the windsock itself remains the same object. The heliosphere behaves similarly on a vastly larger scale. Only instead of responding to Earth's atmosphere, it responds to the enormous weather of the galaxy. Every passing cloud of interstellar gas, every fluctuation in magnetic pressure, every change in the solar wind leaves its signature upon the boundary surrounding our cosmic home. Perhaps the most remarkable realization is philosophical rather than scientific. For centuries, humanity imagined the solar system as an isolated island floating quietly through empty space. Voyager revealed something profoundly different. Our planetary system is not isolated. It is immersed in a living galactic environment. The Milky Way does not merely surround the solar system. It actively shapes it. Every second, invisible forces from distant stars help determine the size and form of the protective bubble surrounding Earth itself. The boundary of the solar system is therefore not defined solely by our Sun. It is co-authored by the entire galaxy, and if its shape can change, then perhaps its position can change as well, because the heliosphere is not simply distorted. It is alive, it expands, contracts, breathes, and in the next chapter, we will discover that the solar system's invisible shield is far from fixed. It pulses with the rhythm of the Sun itself. Imagine standing on a quiet beach. Far in the distance, the horizon appears fixed, permanent, unchanging. But as the tide rises and falls, the shoreline slowly advances and retreats. Sometimes the sea reaches your feet. Hours later, it has withdrawn hundreds of yards. The coastline itself has not disappeared. It has simply moved. For much of the 20th century, scientists imagined the heliosphere very differently. The solar system's invisible shield was often portrayed as a rigid bubble floating through interstellar space. Its shape might not be perfectly spherical, but it was generally assumed to remain stable. Once the heliopause formed, it would stay in roughly the same place. Voyager changed that picture forever. The spacecraft revealed that the boundary of the solar system is not fixed. It moves, it expands, it contracts. Like a giant lung, it slowly breathes. To understand why, we must return once again to the source of everything inside the heliosphere, the Sun. Although the Sun appears remarkably constant to us on Earth, it is actually a variable star. Its brightness changes only slightly over time, but its magnetic activity rises and falls in a remarkably regular rhythm. This rhythm is known as the solar cycle. On average, one complete cycle lasts about 11 years. It is driven by the gradual evolution of the Sun's magnetic field, which continuously twists, stretches, and eventually reverses itself. Every 11 years, the magnetic north and south poles of the Sun exchange places. Then, another 11 years later, they reverse again. Completing a full magnetic cycle requires approximately 22 years. This invisible magnetic heartbeat governs nearly every aspect of the Sun's behavior. During periods of low activity, known as solar minimum, the Sun appears relatively calm. Only a handful of sunspots dot its surface. Solar flares become infrequent. Coronal mass ejections occur less often. The solar wind continues flowing outward, but its overall pressure is comparatively weak. Then, gradually, activity begins increasing. Magnetic fields become increasingly tangled. Dark sunspots multiply across the solar surface. Immense loops of plasma rise high into the corona. Powerful eruptions hurl billions of tons of charged particles into space. Eventually, the Sun reaches solar maximum. At this stage, the star becomes dramatically more active. Solar flares erupt with greater frequency. Coronal mass ejections become common. High-energy particles flood outward in enormous bursts. The Sun seems almost restless, releasing tremendous amounts of magnetic energy into the solar system. From Earth, these changes can produce spectacular auroras dancing across polar skies. For astronauts, they increase radiation risks. For satellites, they threaten electronics and communications. Yet their influence extends far beyond Earth's orbit. Every increase in solar activity strengthens the pressure exerted by the solar wind. Imagine inflating a balloon. As more air enters, the balloon expands. Reduce the pressure inside and it slowly shrinks. The heliosphere behaves in a surprisingly similar manner. The solar wind continuously pushes outward against the surrounding interstellar medium. When solar activity intensifies, that outward pressure grows stronger. The heliosphere gradually expands. When activity weakens, the pressure decreases. The surrounding galaxy pushes inward. The heliosphere contracts. This expansion and contraction does not happen overnight. The solar system is simply too large. Changes, beginning near the Sun, require months, and often years, to travel outward across billions of miles. The solar wind itself moves rapidly, but even at hundreds of miles per second, it needs a long time to reach the distant frontier where the heliopause resides. Consequently, the outer boundary of the heliosphere is always responding to conditions that existed at the Sun years earlier. The edge of the solar system is, in a sense, reading yesterday's weather. This delay creates a fascinating dynamic. The Sun may already have entered a new phase of activity, while the heliopause is still responding to an older one. Like a giant ocean swell crossing the Pacific long after the storm that created it has ended, changes in solar pressure propagate slowly through interplanetary space. The result is a boundary that never truly stands still. Instead, it continuously shifts inward and outward. Early theoretical models suggested these movements might amount to several astronomical units. Modern simulations indicate the variations can sometimes be even greater, depending on solar conditions and the pressure of the surrounding interstellar medium. Remember that 1 astronomical unit equals the average distance between Earth and the Sun. about 93 million miles. Even a small change represents an almost unimaginable distance. Yet the heliopause can migrate by many millions of miles over the course of a solar cycle. This realization transformed how scientists interpret Voyager's historic journey. Originally, researchers imagined the spacecraft approaching a stationary frontier. Instead, the frontier itself was moving. The destination was never standing still. One of the most intriguing discoveries came as Voyager 1 neared the heliopause. During 2012, its instruments detected repeated changes in energetic particles. Galactic cosmic rays would suddenly increase. Solar particles would decline. Then, unexpectedly, the pattern would partially reverse. At first, researchers struggled to understand what they were seeing. Had Voyager crossed into interstellar space, or had it not? The answer gradually became clear. The heliopause itself was moving. Rather than crossing a perfectly stable boundary once and forever, Voyager encountered a frontier that oscillated around the spacecraft. Imagine standing near the shoreline during high tide. A wave rushes past your feet. Moments later, it retreats. Then another arrives. For a short time, you repeatedly move between land and sea without taking a single step. Voyager experienced something remarkably similar. The spacecraft remained almost motionless compared to the immense scale of the heliopause's fluctuations. Instead, the boundary itself swept back and forth. Some scientists describe this behavior as the spacecraft being temporarily engulfed again by the heliosphere before finally emerging into interstellar space. It was a powerful reminder that the heliopause is not a rigid shell. It is an active interface responding to changes propagated outward from the Sun. These changes travel through the solar system as enormous pressure disturbances. When particularly strong solar eruptions occur, they launch powerful waves into the solar wind. Over time, these disturbances merge into gigantic structures known as global merged interaction regions. They resemble enormous shock fronts moving through the heliosphere. As they expand outward, they compress plasma ahead of them, carrying enhanced magnetic fields across billions of miles. Eventually, many reach the heliopause itself. When they arrive, they can temporarily push the boundary farther into interstellar space. Other disturbances produce the opposite effect. The heliopause therefore responds not only to the regular 11-year solar cycle, but also to individual episodes of intense solar activity. In some ways, it behaves less like a solid border and more like the surface of a vast ocean responding to distant storms. Even after those disturbances leave the Sun, their effects continue rippling across the solar system for years. This dynamic behavior explains why modern heliophysicists rarely describe the heliosphere as a static object. Instead, they increasingly view it as a living plasma system. Every second, countless interactions occur between the solar wind and the interstellar medium. Magnetic fields reconnect, shock waves propagate, charged particles accelerate, pressure gradients evolve. The heliosphere continuously adjusts to these changing conditions. Its shape today is not precisely the shape it possessed 5 years ago, nor will it be identical 5 years from now. It is a structure in perpetual motion. This shift in perspective represents one of Voyager's greatest scientific legacies. The mission did not simply reveal where the heliopause exists. It demonstrated that the heliopause itself is dynamic. The solar system possesses weather on a scale almost impossible to imagine. Just as Earth's atmosphere experiences storms, high-pressure systems, and changing seasons, the heliosphere experiences long-term cycles driven by the Sun's magnetic activity. The entire protective bubble surrounding our planetary system slowly inhales and exhales. Its breathing occurs over years rather than seconds, but the principle remains surprisingly familiar. This realization also answers an important question often asked by the public. How far away is the edge of the solar system? At first glance, the question seems straightforward. Surely there must be a single number, one distance marking the end of the sun's influence. Yet Voyager taught us that no such universal distance exists. The heliopause may lie approximately 120 astronomical units from the sun in one direction during one phase of the solar cycle. Elsewhere, it may be significantly closer or farther away. Years later, the same location may have shifted again. The boundary depends upon solar activity, interstellar pressure, magnetic fields, local plasma conditions, and the direction being measured. There is no single radius describing the heliosphere. Instead, there exists an ever-changing three-dimensional frontier. Even sophisticated computer simulations must constantly update their predictions as new observations become available. This is why maps of the heliosphere continue evolving. They are snapshots rather than permanent blueprints. Each represents the solar system at one particular moment in an endlessly changing cosmic environment. Perhaps the most remarkable implication is philosophical. For centuries, humans preferred neat boundaries, maps with clear edges, defined borders, simple geometries. Nature rarely offers such convenience. Instead, reality favors complexity. The boundary surrounding our solar system is not a geometric figure drawn with a compass. It is the visible consequence of countless invisible interactions unfolding across billions of miles. It reflects the changing heartbeat of the sun itself. Every sunspot, every magnetic reversal, every solar flare, every coronal mass ejection ultimately contributes to shaping the frontier, protecting every planet within our cosmic neighborhood. In this sense, the heliosphere resembles a living organism more than a machine. It responds, adapts, expands, contracts. Its motions are slow beyond ordinary human perception, yet over years and decades they become unmistakable. Voyager happened to arrive at exactly the right moment in history to witness this extraordinary behavior. The spacecraft taught us that the solar system is not enclosed inside a rigid shell frozen in space. Instead, it exists inside a vast magnetic bubble whose boundaries are constantly rewritten by the changing activity of its parent star. But another question still remained unanswered. If the sun's own activity can reshape the heliosphere from within, what invisible forces are reshaping it from the outside? Because beyond the heliopause lies an even greater influence, the immense pressure of the Milky Way itself, quietly sculpting the boundaries of our cosmic home from every direction. For decades, people imagined that one extraordinary photograph would reveal the edge of the solar system. A dramatic image, a glowing wall suspended in darkness, a clear dividing line between the sun and the stars. But that moment never came. There was no photograph, no spectacular video, no final panoramic view before Voyager entered interstellar space. Instead, one of the greatest discoveries in the history of space exploration arrived as columns of numbers. Tiny changes hidden inside streams of digital signals, traveling for nearly 20 hours across billions of miles before finally reaching Earth. To most people, they looked meaningless. Rows of decimals, magnetic field strengths, particle counts, radio frequencies. Yet to the scientists waiting patiently at NASA's Jet Propulsion Laboratory, every number represented another clue from a place no human technology had ever visited before. Voyager did not carry eyes. It carried instruments, and those instruments could perceive a universe completely invisible to human senses. The remarkable story of the heliopause was written not in pictures, but in data. Among the most important instruments aboard both spacecraft was the magnetometer, often simply called the MAG instrument. Its purpose sounds deceptively simple: measure magnetic fields. In reality, it performs one of the most delicate scientific tasks imaginable. Magnetic fields in deep space are astonishingly weak. Far weaker than the magnetic field surrounding Earth. Far weaker than the magnets holding photographs to a refrigerator door. Yet these faint fields govern the motion of charged particles across billions of miles. The Voyager magnetometers detect both the strength and the direction of these invisible fields with extraordinary precision. As long as the spacecraft remained inside the heliosphere, they traveled through magnetic fields carried outward by the solar wind. These fields followed the characteristic Parker spiral created by the Sun's rotation. Scientists expected that once Voyager crossed the heliopause, the magnetic field direction would change dramatically. After all, outside the solar system, the field should belong to the Milky Way rather than the Sun. But science often rewards curiosity with surprises. When Voyager 1 crossed the heliopause in August 2012, researchers immediately noticed that the magnetic field became stronger. Yet its direction changed far less than anticipated. For weeks, confusion spread throughout the scientific community. Had Voyager truly crossed the heliopause? Or was it still somehow inside the heliosphere? The magnetometer alone could not answer the question. Instead of providing certainty, it created an even greater mystery. Fortunately, Voyager carried other instruments capable of examining the environment from completely different perspectives. One of the most valuable was the cosmic ray subsystem, commonly abbreviated as CRS. If the magnetometer listened to invisible magnetic fields, the cosmic ray subsystem counted some of the fastest particles in the universe. These particles originate from two very different sources. One population comes from our own Sun. Solar energetic particles are accelerated during flares, coronal mass ejections, and other episodes of intense solar activity. The second population comes from far beyond the solar system. These are the galactic cosmic rays, atomic nuclei accelerated by exploding stars, shock waves, and perhaps even the environment surrounding black holes. For decades, Voyager measured both populations simultaneously. Inside the heliosphere, solar particles dominated. The heliosphere acted as a giant magnetic shield, reducing the number of incoming galactic cosmic rays. Then, during 2012, everything changed. Almost overnight in scientific terms, the detectors recorded a dramatic collapse in solar energetic particles. At the same time, galactic cosmic rays surged to levels never previously observed by the spacecraft. It was as though Voyager had stepped from one invisible ocean into another. Imagine driving through a tunnel during heavy rain. Inside the tunnel, raindrops almost disappear. The moment you emerge on the other side, rain suddenly surrounds your vehicle again. Nothing about the rain itself changed, only your environment. Voyager experienced something remarkably similar. The spacecraft had moved beyond the protective magnetic umbrella of the heliosphere and into the much harsher radiation environment of interstellar space. For many researchers, this represented the strongest evidence yet that Voyager had finally crossed the heliopause. Yet another crucial instrument would soon provide an entirely independent confirmation: the plasma wave science experiment. Unlike a traditional plasma detector that directly measures the speed and density of charged particles flowing past the spacecraft, plasma wave science listens for natural electrical oscillations traveling through ionized gas. Space is not silent. Charged particles constantly generate tiny electromagnetic vibrations. By measuring their frequencies, scientists can calculate the density of the surrounding plasma with remarkable accuracy. This technique would prove invaluable. Ironically, Voyager 1's dedicated plasma science instrument had stopped functioning many years earlier because of an electrical failure. At first glance, this appeared disastrous. How could researchers determine whether Voyager had entered interstellar plasma without a working plasma detector? Nature unexpectedly provided the answer. Occasionally, enormous coronal mass ejections erupt from the Sun. These giant explosions launch shock waves that continue expanding across the solar system for months or even years. Eventually, some reach Voyager's location. When one of these powerful shock fronts encountered the plasma surrounding Voyager, it caused the local electrons to oscillate. The plasma wave science instrument recorded those oscillations. Their frequency revealed the plasma density directly. The results astonished researchers. The plasma density outside the heliosphere was nearly 40 times greater than the extremely rarefied solar wind surrounding Voyager immediately beforehand. Although interstellar space remains an extraordinary vacuum by everyday standards, it was significantly denser than the expanded solar wind at the edge of the heliosphere. This increase matched theoretical predictions almost perfectly. Suddenly, multiple lines of evidence converged. Galactic cosmic rays increased. Solar energetic particles collapsed. Plasma density rose dramatically. The spacecraft had entered an entirely new environment. One remarkable aspect of scientific discovery is that independent measurements carry far greater weight than any single observation. Suppose only the cosmic ray detector had recorded unusual changes. Researchers might reasonably wonder whether an unknown solar event caused the anomaly. Suppose only plasma density had increased. Perhaps local turbulence explained the measurement. But when entirely different instruments, designed independently, operating according to different physical principles, all point toward the same conclusion, confidence grows enormously. That is precisely what happened with Voyager. Each instrument told part of the story. Together, they revealed the whole picture. The magnetometer described magnetic fields. The cosmic ray subsystem counted energetic particles. The plasma wave science experiment measured plasma density. Each observed a different property of the same invisible frontier, and all agreed that something fundamental had changed. Voyager had crossed into interstellar space. When Voyager 2 reached the heliopause in November 2018, scientists gained an extraordinary opportunity. For the first time, they could compare two independent crossings made by two separate spacecraft, traveling through different regions of the heliosphere. Unlike Voyager 1, Voyager 2 still possessed a functioning plasma science instrument. This allowed researchers to measure the solar wind directly as it slowed, weakened, and finally disappeared near the heliopause. The transition unfolded almost exactly as decades of theoretical models had predicted. The solar wind velocity fell dramatically. Interstellar plasma became dominant. Particle populations shifted. Magnetic fields changed. The observations beautifully confirmed the conclusions drawn from Voyager 1. The two spacecraft effectively verified one another. This mutual confirmation ranks among the greatest strengths of the Voyager mission. Scientific discoveries become far more convincing when reproduced independently. Voyager 1 alone might have represented an unusual case. Voyager 2 demonstrated that the phenomenon was real. Yet the second crossing also revealed important differences. The heliopause did not occur at precisely the same distance. Its structure appeared somewhat different. The surrounding plasma behaved differently in subtle ways. These variations suggested that the heliosphere itself changes over time and from one direction to another. Instead of a smooth spherical shell, the boundary proved to be dynamic and asymmetric. Even today, scientists continue examining the enormous Voyager data archive. Many questions remain unanswered. One of the most intriguing concerns, the magnetic field itself. Why did Voyager 1 observe such a relatively smooth transition in magnetic field direction across the heliopause? Early theoretical models had predicted a much sharper rotation. Although later simulations incorporating realistic interstellar magnetic fields explain much of this behavior, researchers still debate the detailed physics governing the interaction. Another puzzle involves energetic particles. Exactly how are some particles accelerated near the heliopause? Why do certain populations appear unexpectedly intense? Which physical mechanisms dominate this acceleration? Shock waves? Magnetic reconnection? Plasma turbulence? Or some combination of all three? The answers remain incomplete. Researchers are also investigating the remarkable structure of the heliosheath. Rather than behaving as a simple buffer zone, it appears filled with enormous magnetic fluctuations and complex plasma interactions that are only beginning to be understood. Computer simulations continue improving as new mathematical techniques become available. Yet no simulation perfectly reproduces every Voyager observation. Reality remains richer than theory. Perhaps the greatest mystery concerns the heliosphere as a whole. Voyager sampled only 2 narrow paths through an object spanning billions of miles. Imagine attempting to reconstruct the entire shape of Earth's oceans using observations from only 2 ships sailing in different directions. Their measurements would be extraordinarily valuable, but they would never tell the complete story. The same challenge faces heliophysicists today. Voyager has shown us 2 remarkable slices through the heliosphere. The rest must still be inferred from remote observations, theoretical models, and future missions. This is why NASA's Interstellar Boundary Explorer, the Interstellar Mapping and Acceleration Probe, and proposed interstellar probes remain so important. Each promises to add new pieces to a puzzle that Voyager first revealed. More than 4 decades after their launch, the twin spacecraft continue transforming our understanding of the solar system. They have traveled farther than any human-made objects in history. Their power supplies continue slowly fading. Their instruments grow colder each year. Eventually, one by one, those instruments will fall silent. The final signals will disappear into the darkness. Yet the scientific legacy of Voyager will endure for generations. Every byte of data transmitted across billions of miles has become part of humanity's permanent record. Those numbers changed how we define the boundary of the solar system. They revealed that interstellar space is not merely an abstract concept. It is a measurable physical environment with its own plasma, magnetic fields, and energetic particles. Most importantly, they taught us that the greatest discoveries do not always arrive as spectacular images. Sometimes they appear quietly, inside columns of numbers, waiting patiently for someone to recognize that the universe has just revealed another one of its secrets. And even after decades of analysis, those numbers continue asking new questions. Because the deeper scientists look into Voyager's data, the more they realize that the invisible frontier surrounding our solar system is shaped not only by the Sun, but also by the immense and ever-changing forces of the galaxy beyond. If the solar system were drifting through a perfect vacuum, its invisible protective bubble might indeed resemble the smooth sphere once depicted in textbooks. There would be nothing to oppose the solar wind, nothing to reshape the heliosphere, nothing to challenge the outward flow of plasma from our sun. But the universe is rarely so accommodating. Space between the stars is not empty. It is alive, filled with invisible gas, charged particles, magnetic fields, shock waves, and the lingering remains of ancient stellar explosions. The heliosphere does not exist in isolation. It exists within an immense galactic environment that is constantly pushing back. For every particle flowing outward from the Sun, another force presses inward from the Milky Way. The true shape of the solar system is therefore not determined by the Sun alone. It is the result of an ongoing struggle between 2 enormous cosmic domains, a silent conflict unfolding every second across billions of miles, an invisible war between a single star and an entire galaxy. To understand that war, we must first leave the familiar territory of the solar system and enter the environment surrounding it. Astronomers call this region the local interstellar medium, or simply the LISM. The name sounds technical, but its meaning is surprisingly straightforward. It is the thin mixture of matter occupying the space between nearby stars. Unlike Earth's atmosphere, the local interstellar medium is extraordinarily sparse. A single cubic centimeter may contain only a fraction of one atom. If such a vacuum existed inside a laboratory on Earth, it would rank among the emptiest environments ever created. Yet the local interstellar medium extends across trillions of miles. Even an incredibly small density becomes significant over such immense distances. This region consists primarily of hydrogen and helium. Some atoms remain electrically neutral. Others exist as ionized plasma. Tiny dust grains drift slowly through the galaxy. Cosmic rays pass continuously in every direction. Magnetic fields thread invisibly through the entire region. It is not empty space. It is a cosmic ocean, and our solar system is sailing directly through it. The Sun currently resides inside a structure known as the local interstellar cloud, sometimes called the local fluff. This cloud spans roughly 30 light-years and appears to be embedded within a much larger cavity known as the local bubble, likely created by multiple supernova explosions millions of years ago. Those ancient stellar catastrophes helped shape the environment surrounding our solar system long before Earth itself developed complex life. Every second, as the Sun races through this cloud, it encounters particles that have wandered between stars for millions of years. Some may have originated inside stars that disappeared before humanity existed. Others may have traveled across entire spiral arms of the Milky Way. Eventually, they meet the outward flow of the solar wind. That encounter creates the heliosphere. One might imagine the local interstellar medium behaving like an ordinary gas. In reality, it is governed by something even more important: magnetism. Threaded throughout the interstellar medium is the interstellar magnetic field. Although unimaginably weak compared with magnetic fields produced in laboratories, it stretches across enormous regions of space. Over distances measured in light years, its influence becomes profound. Unlike solid objects, plasma responds immediately to magnetic forces. Charged particles spiral around magnetic field lines. They accelerate, scatter, exchange energy. The magnetic field effectively guides the motion of plasma throughout the galaxy. This means the heliosphere is not simply colliding with gas. It is interacting with an enormous magnetic structure extending across interstellar space. Imagine trying to inflate a balloon underwater. Now imagine that the water itself is flowing, while invisible currents pull the balloon in different directions. That analogy remains vastly simpler than reality, yet it captures an important truth. The heliosphere exists inside a medium that is both fluid and magnetic simultaneously. Every change in the surrounding magnetic environment alters the balance of forces acting upon the solar system. One of the greatest revelations of the IBEX mission was that the orientation of this interstellar magnetic field appears to exert tremendous influence over the heliosphere's shape. Rather than allowing the solar wind to expand equally in every direction, magnetic tension channels plasma flows into preferred paths. Some regions become compressed. Others stretch. Still others twist into unexpected geometries. Magnetic pressure proves just as important as ordinary gas pressure, perhaps even more so. Meanwhile, another powerful influence never stops acting upon the heliosphere: the motion of the Sun itself. Our star is not resting quietly inside the Milky Way. It orbits the galactic center at approximately 828,000 kilometers per hour, carrying every planet, moon, asteroid, and spacecraft along with it. Earth's yearly orbit around the Sun feels fast. Yet compared with our galactic journey, it is only one component of a much larger voyage. The entire solar system continuously plows through the local interstellar medium. This motion creates what physicists call dynamic pressure. Dynamic pressure depends upon both velocity and density. Even though the interstellar medium is extraordinarily thin, the Sun's tremendous speed ensures that the resulting pressure cannot be ignored. The situation resembles a swimmer moving through water. The faster the swimmer travels, the greater the resistance pushing against the front of the body. Likewise, the leading edge of the heliosphere constantly experiences a headwind generated by the solar system's motion through the galaxy. This headwind compresses the front of the heliosphere. The effect is subtle on human scales. It becomes dramatic across billions of miles. Yet dynamic pressure tells only part of the story. Magnetic fields generate another entirely different kind of force: magnetic pressure. Unlike ordinary gas pressure, magnetic pressure originates from energy stored within magnetic fields themselves. As interstellar field lines encounter the heliosphere, they resist deformation. They bend, stretch, store energy, push back. The solar wind attempts to expand outward. The interstellar magnetic field resists. An invisible equilibrium develops. Modern heliophysics increasingly recognizes that magnetic pressure may shape the heliosphere as strongly as the physical motion of interstellar gas. Perhaps the boundary surrounding the solar system is less like a balloon and more like a drop of ferrofluid suspended inside an invisible magnetic field. The complexity deepens further because much of the hydrogen surrounding the heliosphere remains electrically neutral. Neutral hydrogen behaves differently from plasma. Because it carries no electric charge, magnetic fields cannot guide it directly. Instead, these atoms pass relatively freely across the heliopause. Some enter the heliosphere. Others leave it. Along the way, many exchange electrons with charged particles through a process called charge exchange. This seemingly simple interaction dramatically alters the behavior of both populations. Energetic neutral atoms are created. Fast ions become slow atoms. Slow atoms become energetic ions. An entirely new particle population emerges. These energetic neutral atoms proved crucial for one remarkable spacecraft, NASA's Interstellar Boundary Explorer, or IBEX. Unlike Voyager, which physically traveled through only 2 narrow regions of the heliosphere, IBEX remained near Earth. Instead of crossing the boundary itself, it observed energetic neutral atoms arriving from every direction. Because neutral atoms travel in straight lines unaffected by magnetic fields, they preserve valuable information about the locations where they originated. By counting these particles, IBEX effectively created the first global map of the heliosphere. The mission soon revealed something nobody expected: a narrow band of unexpectedly intense energetic neutral atoms stretching across the sky. Scientists named it the IBEX ribbon. Its discovery immediately became one of the greatest mysteries in heliophysics. Why should one particular region surrounding the heliosphere produce so many energetic neutral atoms? Numerous explanations have been proposed. Perhaps the ribbon marks locations where the interstellar magnetic field aligns in a special orientation. Perhaps it reflects particles temporarily trapped outside the heliopause before returning. Perhaps entirely different plasma processes remain undiscovered. More than 15 years after its discovery, no single explanation has achieved universal acceptance. Yet, the ribbon transformed our understanding of the heliosphere. It demonstrated that the surrounding interstellar magnetic field plays a far greater role than previously imagined. As observational data accumulated, theorists turned increasingly toward supercomputers. The mathematics governing plasma and magnetic fields cannot be solved with pencil and paper alone. Researchers therefore employ sophisticated magneto-hydrodynamic simulations, combining Maxwell's equations with fluid dynamics across 3-dimensional computational grids containing millions, even billions, of calculation points. These simulations recreate the interaction between the solar wind and the local interstellar medium. By adjusting variables such as magnetic field strength, hydrogen density, plasma temperature, and solar wind pressure, scientists generate virtual heliospheres and compare them with observations. Remarkably, different assumptions produce dramatically different shapes. Some simulations generate the classic comet-like tail extending behind the Sun. Others produce a much shorter, broader structure. Still others suggest two powerful plasma lobes extending rearward like the shape of a croissant rather than a comet. Each model successfully explains certain observations while struggling with others. This is one reason why the heliosphere's exact geometry remains one of modern space physics' most active debates. To the public, scientific disagreement sometimes appears unsettling. In reality, it often signals healthy progress. Researchers disagree not because they doubt the existence of the heliosphere. They disagree because the available evidence remains incomplete. Voyager sampled only two trajectories. IBEX observes energetic neutral atoms from afar. Ground-based astronomy contributes additional constraints. Each provides pieces of an enormous three-dimensional puzzle. No mission has yet viewed the heliosphere from outside. Until such an observation becomes possible, multiple interpretations will continue competing. That competition drives better theories, better simulations, better experiments, and ultimately better understanding. The next major step in this journey is already underway. NASA's Interstellar Mapping and Acceleration Probe, known as IMAP, has been designed to build upon the success of IBEX with dramatically improved sensitivity and resolution. Where IBEX provided the first rough sketch of the heliosphere, IMAP aims to produce a far more detailed portrait. Its instruments will detect energetic neutral atoms across broader energy ranges while simultaneously monitoring the solar wind before it leaves the inner solar system. This combination allows scientists to connect changes at the Sun directly with later changes observed near the heliosphere's distant boundary. In effect, IMAP will monitor both ends of the same story. Researchers hope these observations will answer some of the field's most persistent questions. What truly creates the IBEX ribbon? How exactly does the interstellar magnetic field shape the heliosphere? Does the solar system possess a long tail, two plasma jets, or an entirely different geometry still hidden from present models? The answers remain unknown, yet each new mission narrows the possibilities. Perhaps the most extraordinary realization is that the solar system itself is not the dominant force in this story. For centuries, we imagined the Sun shaping everything around it. Voyager, IBEX, and modern simulations reveal a more balanced picture. The Milky Way shapes the Sun as well. Our star pushes outward with the solar wind. The galaxy pushes inward with plasma, magnetic fields, neutral hydrogen, and dynamic pressure. The heliosphere is born where these opposing influences meet. Its shape records the outcome of an invisible negotiation, taking place every second across billions of miles. This silent contest has no winner. The Sun never fully overcomes the galaxy. The galaxy never completely crushes the Sun's influence. Instead, both exist in continuous balance. A balance that shifts with every solar cycle, every interstellar fluctuation, every magnetic disturbance passing through our region of the Milky Way. The true boundary of the solar system is therefore not carved into space like the shoreline of a continent. It is a living frontier shaped by forces both local and galactic, and as remarkable as Voyager's discoveries have been, they represent only the beginning. Because the greatest lesson of this invisible war is not that we have solved the mystery of the heliosphere. It is that we have finally learned how much of the mystery still remains. For nearly half a century, Voyager 1 and Voyager 2 have been carrying humanity's curiosity into the darkness beyond the planets. They have traveled farther than any spacecraft in history, far beyond the orbit of Neptune, far beyond the Kuiper Belt, far beyond the heliopause. Today, they are drifting through interstellar space, billions of miles from Earth, moving silently between the stars. Every day, they become more distant. Every day, their signals grow weaker. Yet every day, they continue telling us something no other spacecraft can. What lies beyond the protective bubble of our Sun? But even these extraordinary explorers cannot travel forever. Every mission eventually reaches its final chapter. The question is not whether Voyager will one day fall silent. The question is, when? Unlike satellites orbiting Earth, Voyager cannot recharge its batteries using sunlight. Solar panels would be useless so far from the Sun, where sunlight is hundreds of times weaker than it is near Earth. Instead, both spacecraft rely on radioisotope thermoelectric generators, or RTGs. These remarkable power systems generate electricity from the natural decay of plutonium-238. No moving parts, no combustion, only the steady release of heat produced by radioactive decay. When Voyager launched in 1977, its generators produced enough electricity to power every scientific instrument aboard. But radioactive decay is relentless. Each passing year reduces the available electrical power. Only a few watts disappear annually, yet after decades those losses become significant. To extend the mission for as long as possible, engineers have repeatedly made difficult decisions. Individual heaters have been turned off, backup systems permanently disabled. Some scientific instruments have already fallen silent. Others now operate only intermittently. Mission controllers carefully manage every remaining watt of electricity, almost as though budgeting the final drops of fuel during an impossibly long voyage. Each decision represents a trade-off: preserve communications, or preserve science, maintain navigation, or continue measuring cosmic rays. The spacecraft have become masterpieces of engineering conservation. Far exceeding their original design life, they continue functioning because generations of engineers have learned how to keep aging technology alive under the harshest conditions imaginable. Current projections suggest that most remaining scientific instruments will gradually cease operating during the late 2020s or early 2030s as available electrical power falls below operational requirements. Eventually, only the spacecraft's radio transmitter may remain active. Finally, even that signal will fade. One day, NASA's Deep Space Network will listen and hear nothing. No carrier wave, no engineering telemetry, no scientific measurements, only silence. Yet silence does not mean the end of Voyager's journey. Long after their transmitters die, both spacecraft will continue drifting around the Milky Way for millions of years. Voyager 1 is heading generally toward the constellation Ophiuchus. Voyager 2 is traveling in the direction of Telescopium. Neither spacecraft is expected to approach another star closely for tens of thousands of years. They will become silent monuments to one civilization's first attempt to reach the stars. Inside each spacecraft remains the famous Golden Record, a copper phonograph disc plated with gold, carrying greetings in dozens of human languages, music from cultures around the world, natural sounds from Earth, scientific diagrams, and images of our planet. It is less a message expecting a reply than a time capsule, a reminder that one small species orbiting one ordinary star once became curious enough to send a greeting into the galaxy. But Voyager's scientific legacy is not ending. It is becoming the foundation for the next generation of exploration. One of the most important upcoming missions is NASA's Interstellar Mapping and Acceleration Probe, better known as IMAP. Unlike Voyager, IMAP will not travel toward the heliopause. Instead, it will remain much closer to Earth while observing the heliosphere remotely. At first glance, this may seem like a step backward. In reality, it represents an entirely different strategy. Imagine trying to understand the shape of a forest. Walking through two narrow paths provides valuable information, but only about those specific routes. Flying overhead reveals patterns impossible to recognize from the ground. IMAP serves as that aerial perspective. Its instruments will detect energetic neutral atoms, particles created through charge exchange processes occurring near the heliopause. Because these atoms carry information about the regions where they formed, Scientists can reconstruct increasingly detailed maps of the solar system's invisible boundary. Compared with the earlier IBEX mission, IMAP offers dramatically higher sensitivity, broader energy coverage, and faster observations. Researchers hope it will answer several of the biggest mysteries still surrounding the heliosphere. What creates the mysterious IBEX ribbon? How exactly does the interstellar magnetic field shape the heliosphere? How rapidly does the heliopause respond to changes in solar activity? Most importantly, what does the true three-dimensional heliosphere actually look like? For the first time, scientists hope to build something approaching a genuine three-dimensional map rather than relying primarily upon theoretical simulations. Yet many researchers believe another mission will ultimately be required, one far more ambitious than Voyager itself. For years, NASA has studied the concept of an interstellar probe. Unlike Voyager, whose primary mission focused on the giant planets before unexpectedly continuing into interstellar space, the proposed interstellar probe would be designed from the beginning with one objective: reach the interstellar medium as quickly as possible. Several mission concepts envision a powerful launch combined with gravity assists from Jupiter and advanced propulsion techniques. Traveling much faster than Voyager, such a spacecraft could reach the heliopause in only a few decades instead of more than 40 years. More importantly, it would carry instruments specifically designed to investigate the heliosphere, using everything scientists have learned since the 1970s. Modern detectors possess vastly greater sensitivity. Computers are incomparably more powerful. Communication systems are dramatically more efficient. A dedicated interstellar mission could perform measurements impossible when Voyager was built. It could directly analyze neutral hydrogen populations, measure plasma composition with far greater precision, map magnetic turbulence in unprecedented detail, monitor energetic particle acceleration continuously across the heliopause. Perhaps most importantly, future probes could travel in directions never explored before. Voyager 1 and Voyager 2 sampled only two narrow slices through an object billions of miles across. Imagine attempting to determine the shape of an elephant by touching only its trunk and one rear leg. Those observations would be valuable, but incomplete. The heliosphere presents exactly the same challenge. To reveal its full geometry, humanity must eventually explore multiple directions simultaneously. Scientists envision an era when several interstellar spacecraft leave the solar system along different trajectories. Together, they could transform isolated measurements into a comprehensive three-dimensional portrait of our cosmic neighborhood. Even with these future missions, many questions remain unanswered. Where exactly does the heliosphere end in every direction? Does it possess a long comet-like tail, two magnetic lobes, or a completely different geometry that current models have not yet imagined? How does the heliosphere respond when the solar system enters a different interstellar cloud? How will changing galactic environments affect Earth's radiation shielding over millions of years? What role do turbulent magnetic reconnection events play near the heliopause? How are energetic particles accelerated to such extraordinary energies? Each answer reveals another question waiting beyond it. This is the nature of exploration. The closer we examine reality, the more complex it becomes. Perhaps the most fundamental question concerns whether we will ever determine the heliosphere's exact shape. The honest scientific answer is surprisingly cautious. Perhaps, but probably not with complete certainty. Unlike a mountain or a planet, the heliosphere never stops changing. Its size depends upon the solar cycle. Its structure responds to magnetic fields. Its boundary shifts with interstellar pressure. Every measurement represents only one moment in an evolving system. There may never be a single permanent map of the solar system's boundary. Instead, Future generations may produce dynamic models showing how the heliosphere continuously changes through time. Just as meteorologists forecast Earth's weather, heliophysicists may one day forecast the space weather of the entire solar system. Maps would no longer depict one fixed boundary. They would display a living frontier, expanding, contracting, twisting, responding to both the heartbeat of the sun and the invisible currents of the galaxy beyond. In many ways, this represents a profound shift in perspective. For centuries, maps were symbols of permanence. Borders appeared fixed, coastlines appeared stable. Today we recognize that even continents drift. The atmosphere changes every hour. The oceans never stop moving. Voyager has taught us that the boundary of the solar system belongs in that same category. It is not an object. It is a process, not a wall, but a relationship between our sun and the Milky Way. Every future mission will refine that understanding. Every new observation will replace assumptions with measurements. Every improvement in technology will allow humanity to see farther than ever before. Voyager began this journey. IMAP will continue it. The interstellar probe may one day transform it completely. Yet perhaps the greatest discovery still lies ahead. Not because the universe is hiding its secrets, but because we have only just begun asking the right questions. The frontier beyond the heliopause is no longer merely the edge of the solar system. It has become the next great destination of human exploration. And somewhere beyond that invisible boundary, another discovery is already waiting for the next spacecraft brave enough to leave home behind. When Voyager 1 and Voyager 2 left Earth in 1977, their mission seemed wonderfully ambitious. Explore Jupiter, explore Saturn, perhaps continue a little farther if fortune allowed. No one could know that nearly half a century later, these two small spacecraft would fundamentally change one of humanity's oldest ideas. Not simply where the solar system ends, but what the solar system truly is. For centuries, we imagined our planetary home as a self-contained island centered upon the sun. Its boundaries appeared permanent, predictable, clearly defined. Voyager revealed something far more profound. The solar system is not an isolated structure floating peacefully through empty space. It is part of a much larger living environment, a vast interaction between our star and the Milky Way itself. The heliosphere is not a rigid shell surrounding the planets. It is a dynamic frontier, constantly reshaped by solar wind, magnetic fields, interstellar plasma, and the endless motion of our sun through the galaxy. It expands, it contracts, it bends, it responds. In many ways, it behaves less like a machine and more like a living system adapting to the environment around it. That realization may be Voyager's greatest scientific legacy. The boundary of the solar system cannot be described by a single distance. There is no universal number that marks the exact end of our cosmic neighborhood. Ask where the heliopause lies, and the answer depends on the direction you travel. It depends on the activity of the sun. It depends on conditions in the surrounding interstellar medium. It even depends on when the measurement is made. The frontier itself is always changing. For generations, science sought certainty in fixed maps and precise boundaries. Voyager taught us that nature often chooses something more elegant, not permanence, but balance. The heliosphere exists because two enormous forces continuously meet: the outward breath of one ordinary star and the inward pressure of an entire galaxy. Neither side completely dominates. Instead, they create a frontier that is forever negotiating its position. Even after decades of extraordinary discoveries, many mysteries remain. Scientists still debate the heliosphere's exact three-dimensional shape. Does it possess a long comet-like tail, twin plasma lobes, or a geometry more complex than current models can reproduce? We still do not fully understand how magnetic fields sculpt its boundaries, how energetic particles are accelerated near the heliopause, or how future changes in the interstellar environment may reshape the solar system over millions of years. These unanswered questions do not represent failure. They represent opportunity. Every generation inherits its own horizon. For earlier explorers, that horizon lay across unknown oceans. For the Apollo astronauts, it lay upon the moon. For Voyager, it lay at the invisible frontier between our star and the galaxy beyond. For the generations to come, that frontier will move even farther outward. New observatories, more powerful space telescopes, the IMAP mission, future interstellar probes. Perhaps one day, spacecraft traveling hundreds of astronomical units from the Sun. Each mission will add another piece to the picture, not replacing Voyager, but building upon the path it first opened. That is how science moves forward, not through one final answer, but through thousands of questions connected across generations. Perhaps this is the deepest lesson hidden inside Voyager's extraordinary journey. Every time humanity believed it had reached an edge, it discovered another frontier beyond it. The planets were not the end. The heliopause was not the end. Even interstellar space is not the end. Each boundary simply became the beginning of a larger map, and perhaps that is true not only of the universe, but of knowledge itself. The more we learn, the larger the unknown becomes. That is not a reason for discouragement. It is the reason exploration never truly ends. Somewhere tonight, Voyager 1 continues drifting through the darkness. Voyager 2 follows its own silent path across the galaxy. Their radio signals grow weaker every year. One day, both spacecraft will fall silent forever. No engineer will repair them. No astronaut will retrieve them. Yet their journey will continue, long after humanity has changed. Long after new civilizations may emerge, those two small machines will still carry the story of Earth among the stars. Not because they traveled the farthest, but because they changed the way we see home. Voyager did more than extend the map of the solar system. It transformed our understanding of our place within the Milky Way. It reminded us that our cosmic home is not separated from the galaxy around it. It is shaped by it, protected by it, and connected to it. The boundary of the solar system is therefore more than the limit of the Sun's influence. It is also the frontier of human knowledge. Every mission that crosses it expands not only our maps, but our perspective, and perhaps that is the greatest value of exploration. Not simply to discover what lies beyond the horizon, but to remind us that there will always be another horizon waiting. As long as humanity continues asking questions, there will always be another Voyager ready to begin the journey.